Hello, everyone, and welcome back. In this lesson, we're going to explore confidence intervals, one of the most important concepts in biostatistics. Confidence intervals allow us to estimate population parameters based on sample data. Instead of giving a single number, they provide a range of values, which are the true population parameter, and where the true population parameter is likely to fall. Now, in this lesson, we'll cover constructing confidence intervals, how to calculate a confidence interval, step by step, and also interpreting confidence intervals, what confidence intervals means and how to apply them. Now, by the end of this lesson, you'll understand how to calculate, interpret, and apply confidence intervals in real-world scenarios. Okay, let's get started. Now, first, let's define a confidence interval. A confidence interval is a range of values that is likely to contain the true population parameter, such as a population mean, with a certain level of confidence. For example, if we measure the average blood pressure in a sample of patients and calculate 95% confidence interval of maybe 118 to 122, we can say that we are 95% confident that the true average blood pressure of the entire population falls within range, 118 to 122. Instead of giving a single estimate, confidence intervals provide a margin of error around the estimate, making it more reliable. Now, to construct a confidence interval for a population mean, we use the formula where x bar is the sample mean, z is the z-score based on confidence level, sigma is the population standard deviation, and then square root of the sample size. So you can see the x bar here, the z is the z-score times sigma, which is this symbol here, and the square root of the sample size, n is the sample size. So the steps to construct this confidence interval is to calculate the sample mean, x bar, then find the average of your sample data, then find the standard error of the mean, and the standard error tells us how much our sample mean might vary. Then choose a confidence interval to find the z-score. So the common confidence interval are 90% with a z of 1.645. A 95% confidence interval is a z 1.96, and then 99% confidence interval is a z 2.576. Now we compute the confidence interval by multiplying the z-score from the standard error, add or subtract from the sample mean. So as an example, if we measure the average weight of newborns in a hospital and get a sample mean of 3.2 kilograms with a standard deviation of 0.2 kilograms and a sample size of 100, we can construct a 95% confidence interval to estimate the true average weight of all newborns. So this is how we calculate the sample mean, and then to find the standard error of the mean is the formula SE equals sigma over the square root of n. Now this tells you how much your sample mean might vary if you repeated the sample many times. So you can see the SE here equals sigma over the square root of n. Now to choose a confidence interval and find the z-score, you can see here the 90% is the z-score around 1.645. 95% is 1.96, and 99% is 2.576. So this is where you would input it into the formula. Now to compute the confidence interval, you multiply the z-score by the standard deviation and add or subtract from the sample mean. All right, now let's walk through a real-world example using a confidence interval. Let's say we're trying to estimate the true average weight of newborns in a hospital. We can't measure every newborn, so instead we take a sample. We take a sample of 100 newborns. Now from that sample, we calculate the average weight, or what we call the sample mean, to be 3.2 kilograms. The population standard deviation, which measures how spread out the weights are, is known to be 0.5 kilograms. And we want to be 95% confident in our estimate. That means we'll use a z-score of 1.96 based on the normal distribution. Now we would calculate the standard error. The first step is to calculate the standard error of the mean. This tells us how much our sample mean might vary from the true population mean just by chance. So the formula is the standard error equals sigma over the square root of n. So we plug in the numbers. Now 0.5 divided by the square root of 100. The square root of 100 is 10. So here we have 10. So 0.05 divided by 10 gives us a standard error of 0.05. So that's how we get the 0.05 here. Now we use this confidence interval formula, that is 3.2 plus or minus 1.96 times 0.05. So 1.96 times 0.05 equals 0.098. So the margin of error is about 0.0 kilograms. Now we add and subtract that from the sample mean. 3.2 minus 0.098 gives us 3.102. And 3.2 plus 0.098 gives us 3.298, as you can see here. So our 95% confidence interval from 3.102 kilograms to 3.298 kilograms. What does this mean? This means that we are 95% confident that the true average weight of all newborns in the hospital is somewhere between 3.102 and 3.298 kilograms. Now, if we are to take many more samples, 95% of those intervals would contain the real average weight. Confidence intervals really just give us a range, not just a single guess. They're more honest about the uncertainty that's always present in sample-based research. Now that we know how to construct confidence intervals let's talk about what they actually mean in practice. A common misperception is that 95% confidence interval means that there's a 95% chance that a true population mean is inside the interval. That's not exactly correct here. Instead, it means that if we repeated this experiment many times, 95% of the confidence intervals, this would contain the true population mean. We can be 95% confident that our interval captures the true parameter. Now, one important thing to remember is that the larger sample sizes lead to more precise confidence intervals. Small sample sizes lead to wider confidence intervals where there's more uncertainty. Larger sample sizes narrow the confidence intervals, which are more precise, which leads to more precision. For example, if we estimate the average cholesterol level in a city using a sample of 20 people, our confidence interval might be wide. But if we increase our sample to 500 people, the interval will be much narrower and more precise. Now, confidence intervals are often used in hypothesis testing. If a confidence interval does not include 0, we may conclude that there is a statistically significant difference between groups. For example, if we test a new medicine or medication and find that 95% confidence interval for blood pressure reduction is maybe -10 to -2, we can be confident that the drug has a significant effect because the interval does not include 0. Okay, today we covered constructing confidence intervals, how to calculate a confidence interval step by step, and we also covered interpreting confidence intervals and how to apply confidence intervals. Now, confidence intervals are essential in biostatistics because they allow us to estimate population parameters with a known level of confidence. All right, thanks for watching, and I'll see you in the next video.